testing technology in zero gravity, lunar gravity, or even Martian gravity. Techniques pioneered for the early space program find widespread uses in modern research. At the beginning of 1968, NASA was preparing to launch the unmanned Apollo 5. A Saturn 1B would lift a very different payload to low Earth orbit. It had been 12 months since 3 astronauts were incinerated, preparing for the Apollo 1 launch. Supporters of the American space program feared that inquiries in both houses of Congress, set up after the tragedy, would axe the Apollo program. But President Lyndon Johnson, who had decorated 2 of the Apollo 1 astronauts, had influence on Capitol Hill, and his ongoing support for NASA helped quell any political backlash. Work on a redesigned Apollo capsule was progressing. But the rush to meet President Kennedy's end-of-the-decade deadline sat uncomfortably with the need for precision and quality. All flammable materials had been eliminated from the spacecraft and spacesuits. At launch, the astronauts would no longer breathe pure oxygen, and the complex hatch had been replaced by a one-piece unit that could be opened rapidly. More than 1,400 wiring problems had been corrected. But there was one vital piece of the Apollo program that remained untested. Nothing like it had ever flown. The lunar landing craft, known as the lunar module, had been plagued with development problems, and its first test flight had been delayed by almost 12 months. It consisted of a descent stage that would remain on the Moon and an ascent stage that would return the astronauts to the Apollo command module waiting in lunar orbit. Each part had its own engine. In testing, the descent engine had not been burning smoothly. Of all the Apollo hardware, this engine had to respond to the most delicate control. Rigorous testing finally solved this problem, and LM-1 was prepared for flight. The unmanned Apollo 5 would test the craft in Earth orbit. The lunar module, packed beneath the unique nose cone, had no landing legs, as these would have further delayed delivery. And after pressure tests on LM-5 had blown out a window, LM-1 had aluminium panels instead of glass in its windows.
RTC, will use site select, Guido.
On January the 22nd, 1968, the 2-stage Saturn 1B stood fueled and waiting on Cape Canaveral pad 37B.
7, 6, 5, 4, 3,
Transmitted 5 enter.
Flying start, 5 enter.
Thrust okay. Affirmative. Program 11.
Okay, TLK P11.
Roll pitch start.
Roll in pitch.
This mission would be judged entirely on telemetry, on the electronic flow from sensors monitoring every system in the booster and the lunar module. At the end of the flight, nothing would return to Earth.
Cutoff plus 50.
NASA needed to know how the lunar module's descent and ascent engines would function in space. A software problem shut down a descent engine burn after only 4 seconds, but Mission Control were able to reprogram it. After 11 hours, all systems had been checked, and the mission declared a success. Astronauts would only have one opportunity to fly the craft, and 2 different types of simulator were developed for training. The Lunar Landing Research Facility at Langley exposed astronauts to the kind of decisions they would have to make during the last 50 metres of their descent to the lunar surface. But this was a bit like a carnival ride, and the astronauts preferred the free-flying simulator known as the Lunar Landing Research Vehicle, or LLRV. It was nicknamed the Flying Bedstead. A gimbal jet engine provided partial lift that helped the craft behave as though it was under the influence of lunar gravity. The rest of the lift and the control came from throttleable rockets, similar to those in the lunar module. Just like any other aircraft, it had to be thoroughly tested, and NASA test pilot Joe Walker made the first series of flights in 1964. It could take off and fly using the jet engine and then be switched to sim mode when it would behave like the lunar module. In 1967, Neil Armstrong was the first astronaut to fly the prototype. The following year he flew a modified version with cockpit walls that limited his view to something like he'd see through the lunar module window. When switched into sim mode, the response to pilot control became sluggish, as close as experts could make it to the way the lunar module would behave in lunar gravity. Later, astronauts would call the LLRV the unsung hero of the Apollo program, but NASA administrators were having second thoughts. It would not be the last crash. Of 5 LLRVs and its derivatives, only one was left at the end of the Apollo program. The second Saturn V launch was the final unmanned Apollo mission, Apollo 6. Mission objectives included monitoring the amount of vibration a fully loaded Saturn V would experience. It was carrying a dummy lunar module and a hybrid command and service module. Like Apollo 4, it was not just covered with sensors, but cameras too. Being the first time the Saturn V was carrying a full load, engineers were keen to see how it performed. There were problems. Two minutes into the flight, vibrations ran through the length of the rocket, causing damage to the adapter housing the lunar module. When the second stage took over, 2 of its engines cut out early, affecting the final orbit. The third stage had to burn longer to compensate. Inside the command module, a camera was trained on the window. And at various parts of the astronaut's instrument panel. After 3 orbits, the upper stage failed to reignite as commanded. NASA wanted to test the capsule in a high-altitude, high-speed re-entry, so the command and service module separated from the upper stage and used its own engine to boost it to a higher orbit for a faster re-entry. Though Apollo 6 was troubled with technical difficulties, NASA understood the vibration problems well and was able to redesign various subsystems according to the information gathered during this mission. Finally, NASA was ready to launch another manned mission, and by October 1968, Apollo 7 stood ready for launch. it had a completely redesigned command module, and the astronauts would wear a completely new spacesuit. After the Apollo 1 fire, the new A7L suit was fire-resistant with an outer layer of Teflon-coated beta fabric. A one-piece fishbowl helmet that did away with the need for a visor and a visor seal was fitted to the shoulders, allowing head movement and providing superior visibility. On the morning of October the 11th, 1968, 3 astronauts were prepared for the Apollo program's first manned flight. It would be the program's last Saturn 1B mission and would not carry a lunar module. Veteran of the Mercury and Gemini programs Wally Schirra and 2 first-time astronauts, Don Isley and Walter Cunningham, would be NASA's first astronauts to fly in almost 2 years.
4, 3, 2, we have ignition. Commit liftoff. We have liftoff. This is launch control. We have cleared the tower.
Roger, tower clear. 12 seconds out and the roll program has commenced.
The bigger Apollo capsule provided a more comfortable environment necessary for long-duration flights that were required to get to the moon. The crew could take off or put on their bulky spacesuits as required, and they didn't have to remain in their couches, as in the Mercury and Gemini spacecraft. Soon after reaching orbit, the command and service module separated from the S-4B upper stage. On a moon mission, this would normally house the lunar module. One of the 4 adapter panels had not opened fully. On subsequent flights, these would separate completely from the upper stage. The spacecraft turned around and practiced docking using a visual reference target that would usually be mounted on the lunar module. Not long into the mission, Schirra came down with a cold, and in the confines of the capsule, it quickly spread to the other 2. In zero gravity, the nasal congestion was not clearing in the same way it would on Earth, and the crew were very uncomfortable. Eating became a sore point with the astronauts. Though the food had improved since the earlier space missions, the freeze-dried and bite-sized rehydratable meals fell short of what they considered acceptable. The demands on this mission were considerable. Tense interchanges between the sick astronauts and mission control were not uncommon. They had to fire the service module engine no less than 8 times. Public relations reached new heights on the mission. A series of TV broadcasts from the capsule were watched around the world. At one point, Schirra refused to switch on the TV equipment because the schedule was too crowded and the crew had not eaten. Preparing for re-entry, a new dispute broke out. The astronauts refused to wear their helmets during the return to Earth. With their colds, they worried about the rapid changes in pressure. They wanted to hold their noses and blow to equalise the pressure. Aboard the carrier Essex, the Apollo 7 astronauts were treated as returning heroes, but they did not receive the usual NASA honours, and Schirra, Isley and Cunningham never flew again. Carbon dioxide is a small but vital component of our planet's atmosphere. The carbon that makes up the vast bulk of plant matter is extracted from this atmospheric CO2. In turn, the plants replenish the atmosphere's oxygen. All animal life breathes this oxygen and exhales CO2. This is called the carbon cycle. Our modern industrial societies rely on oxygen as well, and by burning coal and petroleum products, we produce the energy that powers our affluent lifestyles. This process produces carbon dioxide too. There has been a measurable increase in atmospheric CO2 since formal monitoring commenced. Higher levels of CO2 mean that the planet's blanket of air lets less of the Earth's heat escape out into space, prompting a slight rise in the planet's temperature. This has led to visible reductions in the Arctic sea ice and in the retreat of glaciers at the edges of the Antarctic continent. Using weather readings from around the world, NASA's Goddard Institute for Space Studies says that 2014 was the hottest year since 1880. The Goddard report revealed that 9 of the 10 hottest years on record have all been in this century. To understand the geographic distribution of the sources of CO2 and the regions that remove it from the air, NASA commissioned a satellite equipped with an extremely accurate suite of spectrometers to analyse the intensity of CO2 concentrations in the atmosphere. This was the second time NASA had built an orbiting carbon observatory. The initial satellite, OCO, launched in 2009, failed to reach orbit when the payload fairing didn't separate from the spacecraft and it could not achieve orbit. A duplicate orbiting carbon observatory, known as OCO2, successfully went into polar orbit in July 2014. Its north-south orbit allows it to overfly every point on the Earth's surface at least once every 16 days. It makes measurements in 3 different modes. Nadir mode samples the atmosphere directly below it, giving a global picture of the swirling concentrations of CO2. This map from Goddard was compiled using ground-based measurements. Data from OCO2 will deliver far greater detail. A second type of operation, target mode, enables the observatory to focus on a single point of interest, allowing it to gather multiple readings which can be compared with ground measurements made at the same site. The third, glint mode, sees the satellite sample close to the point on the Earth's surface that directly reflects the sun's rays. This further enhances the spectrometer's sensitivity, especially when sampling over the oceans. And OCO2 can detect oxygen concentrations, which will give a clear indication of the growth rates of plants and their ability to act as carbon sinks. OCO2 will remain operational for at least 2 years. In the early 1950s, NASA's predecessor, the National Advisory Committee for Aeronautics, carried out in-flight zero-gravity tests. By flying in a parabolic arc, an aircraft could offset the force of gravity for a short time. Early tests in a Lockheed XP-80 were rudimentary. Flying the precise parabola to maximise the zero-G time was difficult for pilots. It's hard to know what they learned from this kitten experiment. By 1959, at the commencement of NASA's Mercury program, parabolic flight was well understood, and it became a fundamental part of astronaut training. To achieve the effect, the plane climbs at a 45-degree angle. As the thrust is reduced and the aircraft's nose drops, passengers experience weightlessness until the plane's nose reaches a downward angle of 30 degrees when the pilot pulls out of the dive. In the mid-1960s, NASA employed 2 KC-135 aircraft for zero-G training. These are the military version of the Boeing 707. They were nicknamed the Weightless Wonders. During the Gemini program, astronauts were now required to walk in space, and the zero-gravity training flights came into their own. Before Michael Collins made his spacewalk on Gemini 10, he trained extensively in these short bursts of zero-G. In early preparations for the moon landings, the flight paths were altered to simulate lunar gravity. Information gathered on these flights was used to modify spacesuit design to cope with the most difficult situations. Other scenarios worried NASA planners too. If an astronaut wearing his bulky spacesuit and heavy life support system fell over, would he be able to get back to his feet? The aircraft, flying a shallower parabola, was able to simulate lunar gravity for longer durations than for zero-G. Russia's Ilyushin IL-76 serves as the largest zero-gravity aircraft. Today, such planes are used for far more than training astronauts. They serve as microgravity laboratories, where equipment is tested and experiments are undertaken. Operators are even offering zero-gravity joyrides. The European Space Agency, in partnership with Technics, has 6 zero-G campaigns each year flying out of Mérignac Airport in the south of France. The A300 aircraft used for these flights is soon to be replaced by an A310. The rear of the aircraft, known as the free floating area, is padded and fitted with handrails. It is equipped with fixed benches for technical and biological experiments, which are the prime reason for the flights. Recently, the International Space Station began using a 3D printer. To make certain that it would function properly in microgravity, it was first tested aboard this zero-G flight. Human physiology, fluid mechanics, biology, combustion and basic physics are among the most studied disciplines.